section 10.7, which is about complex numbers. So we have three things to do in this section. The first is to introduce complex numbers, which all come from the square roots of negative numbers. Negative numbers. The second is then to look at how do we work with complex numbers. So this is complex number arithmetic. How do we add, subtract, multiply, divide, that kind of thing. And then we're also going to talk about the powers of the imaginary I. So this is of I. And we're actually going to do this out of order because it's good to know the powers of I before we get into the complex number stuff, working with it. But let's talk about that imaginary number. And imaginary spelled with an A there. So the imaginary number comes from the fact that we know we can't take the square root of a negative number. It's not a real number. So the opposite of real is imaginary. Again, us good lazy mathematicians. So that gives us the imaginary I. And then we extend this to the square root of any negative number becomes I times the square root of that number. So up until this point, we've been saying that we can't have negatives under the radical, under an even radical, and now we can. And this is really leading us right into chapter 11. But just a couple quick examples here to see how this property works. Let's say we had something like the square root of negative 36. Using our product property, we can split this into the square root of negative 1 times the square root of 36, which gives us that I times 6, or 6I is how we typically write that. Another one, something like the square root of negative 5. Can't take the square root of 5, so this just becomes I square root of 5. And that's just how it works. And something, let's do one more here. Let's do the negative square root of negative 20. So this is negative times the square root of negative 1 times the square root of 20. So this becomes negative I times, we can split square root of 20 into 4 times 5, so 2 square roots of 5. And this becomes negative 2I square root of 5. So you can see kind of the three different ways that we would go about simplifying radicals with negatives. Either we can take a perfect square and stick a negative on it, so we get 6I, or we can't take the square root and we just pull the I out, or we do a combination of both, or we have to simplify the square root like we always have been doing, and also make sure we pull out the I. So when we are allowing square roots with negatives, our rules change a little bit in the order in which we simplify. So we're going to do a couple, 3, 4 examples here. So let's say we have square root of negative 3 times square root of negative 5. Now, since normally square roots are not supposed to have negatives underneath that radical, we have to get rid of those first before we can start simplifying. So whenever you have negatives, the first step should be to pull the I out. So I square root of 3 times I square root of 5. And the reason we do this is because if we were to allow to just simplify, well, then we would have the square root of -3 times -5, or the square root of 15. But square root of 15 is not the same as I times the square root of 15, or I squared times the square root of 15. So you just want to make sure that you're doing the I first. So if you have a negative under square root, make sure you pull the I out before you do anything else. And then if you think of what I is, it's the square root of -1 squared. So this just becomes square root squared cancels. It's negative square root of 15. Okay, let's try a couple more here. Square root of -5 times the square root of -60. So this becomes I times the square root of 5 times I times the square root of 60. And this is going to be I squared times the square root of 300, or I squared times 10, because 300 is 3 times 100, and the square root of 3. So we know from up here that this becomes -1. So this is -10 square roots of 3. Excuse me. Let me just do a few more here. The square root of -9 times the square root of -1. This is 3i times I, 3i squared. And again, I squared just becomes -1. So this is just -3. And the last little example we're going to do right here is division. So the square root of -27 divided by the square root of 3. Again, just like with the multiplication, you want to make sure you're doing the i's first. So this is I square root of 27 over square root of 3. And so this is I times 3 rad 3, because 27 is 3 times 9, all over square root of 3. Square roots of 3 will cancel here, and this is just 3i. And of course, you can simplify once you get to this point as many ways as you can think of. So we could have combined the radicals in this step instead of simplifying this radical, but you get to the same answer. So before we get into complex numbers, this was just working with some imaginary numbers, because all of these are imaginary, except for that square root 3. So when we get into complex numbers, we need to know and understand how the powers of I, so we're doing powers of I first before we do complex number arithmetic. Powers of I. So since I square root of -1, we saw already that I squared, which is the square root of -1 squared, is just -1. So then if we go to the next power, I cubed, the way that we think about this is I squared times I. I squared is -1, so I cubed is defined as -I. And then for I to the 4th, this is I cubed times I. So this is -I squared. I squared is -1, so this is -1. or just 1. So this is how our powers of I work. We have I to the first equals I squared equals -1, I cubed equals -I, and I to the fourth equals 1. And then once we get to I to the fifth, we can do that here as well. I to the fifth will be I to the fourth times I to the fourth is 1, so this is just I. So you need to know these 4 powers, and then you just look at how far past the next multiple of 4 we are, because now they're going to start to repeat. So I to the fifth is I to the sixth is 2 away from 4, so that means it's going to be -1. I to the seventh is going to be I to the eighth is I to the fourth squared, and so that means that's going to be 1 again, and your pattern restarts. So these are the 4 powers of I that we need to know, so we can calculate any power of I. And we have some tricks to do this fast. So for instance, something like I to the 19th. So you take 19, and you can divide by 4 if you want. But what I look at is, what's the multiple of 4 that's less than this? So we know multiples 4, 8, 12, 16. So this is 16 plus 3. That means that 19 is going to act like I to the third, because we can split I to the 19th into I to the 16th times I to the third. That's our power of exponents. We add exponents with the same base. 16 plus 3 becomes 19. I to the 16th is a power of 4. It's specifically I to the fourth to the fourth. Oops, not times, not plus. Times I cubed. So this becomes 1 times I cubed. And we know I cubed is -I. So we can do it like that. And this is how we handle larger powers of I. So let's, excuse me. Let's take a look at another one here. Let's do something real big like 1107. So we need to know what power of 4 goes into 1107. So you can do that by just dividing 4 into 1107. So 4 goes into 11 twice. 3, bring down the 0. 7 times. 28, bring down the 2. Bring down the 7. 4 goes into 27. 6 times. It's 24 with a remainder of 3. So 1107, or I to the 1107, we can split this into I to the fourth, the 276th times I to the third. Because we know that 1107 has to equal 4 times 276 plus 3. I wrote 277. 276. So once we know this, we can construct this. I to the fourth is 1. 1 to anything is 1. So this is 1 times I cubed again. And that's going to give us -I. So you can do fast powers of I by just dividing by 4. And we typically want to look for 4 because I to the fourth is 1. Excuse me. So let's go ahead and take a look at some complex numbers here. So complex numbers are just, they are numbers that have a real part and an imaginary part. They're complex. They have two different types of parts. And the way that we see these most often is A plus BI. So A and B these are real numbers. So fractions, decimals, whole numbers, whatever we want. And then what makes this complex is that imaginary I. So we can have imaginary numbers that are multiplied by real numbers. Those are still considered imaginary number. And what we find is that every real number is a complex number. So let's write that down, every real number is a complex number. So think of the number 16. I can write 16 as 16 plus 0 times I. So I make B 0 in this format, and I have a complex number. 0 is a real number, so I can do that. So all of the real numbers are housed in the set of complex numbers. Complex numbers are the biggest set of numbers there are. We've talked about real numbers a lot. We know that there's whole numbers. We know that there's fractions. All of those are smaller than complex because everything can be thought of as a complex number when you take that b to equal 0. So with our complex numbers, let's talk about how we add and subtract. Complex numbers. So let's say we have A plus BI plus C plus DI. So the way that we add complex numbers is what we call component-wise or term-wise. So real to real, A plus C, complex to complex, BI plus DI. And then normally what you'll see is these grouped up, A plus C in parentheses, B plus D in parentheses, multiplied by I. And so adding complex numbers is as easy as adding real numbers. You just add real part to real part and imaginary part to imaginary part. And subtraction works the same way. We have A plus BI minus C plus DI. The negative distributes. We subtract A minus C, and then we add BI minus DI. And again, these usually get grouped up with parentheses. B minus DI. And so we're just adding or subtracting the corresponding parts. This and this sit in the same place, this and this sit in the same place. So you add the A and the C, or you subtract the A and the C. Same thing with B and D. So let's try this out on a couple examples. So let's start with 2 plus 3i plus negative 3 plus 2i. And according to our format, this is going to be 2 plus a negative 3 plus 3 plus 2 times I. So we're just taking the corresponding pieces and putting them into this format, real to real, imaginary to imaginary. And then you add those two numbers. And so this becomes -1 plus 5I. Try another one here, some subtraction. Let's do 3 minus 5I minus -4 plus I. So this is going to be 3 minus -4, and then plus -5 minus 1 times I. And this is going to give us 3 plus minus -4 is 3 plus 4, or 7, and then this is going to be minus 6I. And that would be our answer. 7 minus 6I. So, adding, subtracting, not super difficult. It just, you got to get used to matching up the right pieces and putting them together. And then once you get the hang of that, it'll feel a lot like adding and subtracting regular numbers. So multiplying and dividing complex numbers is a little bit different. So let's talk about multiplying first. Multiplying complex numbers. So if we have A plus BI times C plus DI, the way we multiply is we treat I like it's a variable, which means we need to FOIL. So we have A times C, A times DI, BI times C, BCI, and BI times DI, which would be plus BDI squared. Then we can simplify. So you can think of this as 1 FOIL, 2, then simplify. So this is AC plus AD plus BC, and I can factor out the I from that. And then I squared is just -1, so this is minus BD. So we end up with AC minus BD, grouping up those non-imaginary pieces, plus AD plus BC all times I. Now you don't need to remember this, and in fact I would encourage you not to memorize this format, and just know that you need to FOIL and then simplify. And if you do that, it's just like regular binomial multiplication, and we have something like x plus y times 2x plus 3. We just FOIL it out and simplify. And we treat it the same way. So think of your I as a variable first, and then once you've FOILed it, then you can simplify. Let's look at some examples here. So let's start with -7i times 3i. So here there's no FOILing. Right? There's no A and there's no C. So when we do this one, we just multiply straight across like we normally would. Treat I like your variable. -7 times 3 is -21. I times I would be I squared. And then simplify. -21 times -1, because I squared is -1, so this is just +21. the next one here, 3i times 2 minus I. Here we do have some true complex numbers in the general form. So we just FOIL, distribute the 3i. 3 times 2, 6i minus 3i squared. And then we can simplify I squared is negative 1, so this will be positive 3 plus 6i, because this would be 6i minus 3 times negative 1. Okay, let's do one more here. Do 2 plus 3i times 6 minus I. So this one's just like our general form. We're just going to FOIL these out. So we have 2 times 6, 12, minus 2i, plus 18i, and then minus 3i squared. So we have 12 minus 2i and plus 18i, because we're still treating I like a variable, is plus 16i, and then minus 3i squared, just like it was here, would be plus 3. And so we have 15 plus 16i is our final answer. Okay. So multiplying complex numbers, as I said, not any different than multiplying variable expressions like x plus 2 times x minus 3. Just FOIL it out, treat it like it's a variable, the I, that is, treat the I like it's a variable, and then simplify once you've multiplied everything out. Now division, dividing complex numbers, works a little differently. And this comes from the fact that a plus bi over c plus di, these are grouped up. We've talked about this at length in class. The plus here connects each of these two things on the top and bottom to each other, which means we can't simplify the d unless c, a, and b can all be divided by d. Similarly, we can't simplify and cancel the c unless d, b, and a can all be divided by c. So what we do is we rationalize and we always rationalize the denominator. So we multiply by the complex conjugate, c minus di, c minus di. So this is the complex conjugate. And it works just like our conjugates that we saw before. When we were multiplying by conjugates for the radicals. And the reason it works the same way is because I is really a square root. It's the square root of negative 1. It's just a version that we write with a special letter. So you still multiply by the conjugate, this time the complex conjugate. So these should stay the same. You just switch the sign here, plus to minus. Whatever you do to the bottom, you do to the top. And then you simplify. So let's look at a couple examples of this in action. So let's start with 2 plus I over 1 minus I. So our complex conjugate, grouping these up, is going to be 1 plus I and 1 plus I. So for this one, we'll multiply it out. So on the top we have 2 plus 2i, distributing, plus I squared. And on the bottom we have 1 plus I minus I squared. And then we simplify. We have 2 plus 3I minus 1 over 1 minus negative 1. So this gives us 1 plus 3I over 2. And to write it in the proper format, we just divide each by 2, 3 over 2I. So what's happening here is the same thing that happens when we multiply by conjugates with radicals. It forces a very specific factorization, which is 1 minus I squared. When we multiply on this one. Now this is the same factorization for our conjugates when we think about the general one. So complex conjugates. Will always work the same way. So we know A plus B times A minus B, our standard conjugate pairs, becomes A squared minus B squared. That's how we simplified our radicals before. Now if we have complex A plus BI times A minus BI, it doesn't change. A times A is still A squared. It's still going to be minus, and now it's going to be B squared I squared. But I squared is just negative 1. So this becomes A squared minus a negative B squared, or A squared plus B squared. And that's exactly what happened here. 1 plus 1 squared, because our conjugate, or our coefficient here is 1. So you can use this as the pattern. Now if you ever forget, you can always just multiply it out like we did in that example up there in part A. So let's try part B here. We'll do 16 plus 4I over 1/4 I. So our conjugate here is negative I. This should be over 4 over 4. So we distribute up here, we get negative 16I over 4 minus 4I squared over 4, all over negative 1 over 16 I squared. So this gives us negative 4I. 4's cancel, I squared is negative 1 plus 1, all over positive 1 over 16. I squared negative 1 times the negative makes positive. 1 over 16 stays the same. And then we just flip and multiply. And so we end up with 16 minus 64I. And that's just multiplying by the reciprocal here. So this divided by 1/16 is the same as this thing times 16. So let's do one more, and that'll be the end of this section and the end of this chapter. So C, 4 minus I over 3 plus I. So our conjugate pair for 3 plus I will be 3 minus I. 3 minus I. So on the bottom here, we know that from our complex conjugates, this is going to be 9 plus 1, because A is 3 and B is 1. And then up here, we need to actually FOIL. So we have 12 minus 4I minus 3I plus I squared. And then we simplify, and we have 12 minus 7I minus 1 over 10, or 11 minus 7I over 10. And then writing this in proper form, 11/10 minus 7/10 I. So division of complex numbers is really just rationalizing that denominator. We rationalize using conjugates. We call them complex conjugates since we have complex numbers. And you set them up the same way we did regular conjugates. So that's the end of this section and the end of chapter 10.